Gee-Choon, who's going to talk to us about Cartesian magicness of three-dimensional boards.
Okay, good afternoon everyone. Can you all hear me clearly? Yes, okay. Actually, as you can see here, I'm going to talk about something related to magic, which is magic square actually. It's kind of like a generalization of magic square from 2 dimensions to 3 dimensions. And actually, I was trying to solve another problem related to this concept of local anti-magic chromatic number last year. And suddenly this idea came up that I think that I should define something that I call this Cartersian magic over here. Okay? And this is a joint work with Hoken and YG. And it's also partially funded by my university, so that without a small amount of fund, I may not be able to come to join all of you here actually. So I'll begin with this magic square, and we all know that there is a PQ board of P rows and Q columns, and we want to assign the integers from 1 to PQ to all the rectangles, so that every row sum is a constant, say n, and every column sum is another constant, say n. And we know this problem is completely solved quite some time ago, and you can easily find some papers on how to construct magic rectangles by magic approach also. So actually, if we put the rectangles PQ and the transpose of PQ in a 2 by 2 matrix M here, where the big star is a submatrix of suitable size with all 0 entries, then actually we can see that what we want is the sum of all the first P row must be n, and the sum of the next Q row must be n. So with this in mind, I would like to generalize it to a larger dimension for this matrix n. So this is what we have here. We call it K tuple P1, P2 until Pk, P1 to Pk board, or a generalized plane in K space. Here, the entry of this M is Pi Pj, which is a submatrix of size Pi by Pj. And the entry in position Ji is just the transpose of the entries in position Ij. And if I let Mr to be the R row of the matrix M, we say this P1 to Pk board is Kd magic. If the row sum of all the entries of every row of Mr is a constant called Cr, and also the collection of all the C1 to Ck has exactly D distinct elements. So when K is equal to 2, actually you get what we call this magic square or magic rectangles. So we are going to look at what happens when K equal to 3. And when K equal to 3, my D must be 1, 2, or 3. And I call for each different value of D, I call it Cartesian magic, bi-magic, or tri-magic. The reason is because we can actually put the boards PQPR, the board PQR in this way, so that it looks like it's in a 3-dimensional space problem. Okay, let's begin with this Cartesian magic, where I want to let C1, C2, C3 equal to M. And I let S, PQ, PR, and also QR is the sum of integers in PQ, PR, and also QR. And it's quite easy to get 2 simple properties on Cartesian magic problems in terms of the value of PQR and also in terms of M. So using these 2 lemmas, we get 2 results. And the first one shows that the PPPR board, if it is Cartesian magic, then we must have R equal to 1. And when P is equal to 1, surprisingly, there is no Cartesian magic 1QR boards for all the Q and also R. And the proof is actually quite straightforward. The general result that we get for this is that every PPP board is magic. And believe most of us has an idea about what is super magic. And if you know that KPPP is super magic, then I believe you also can see that it is corresponding to the PPP board is Cartersian magic. In other words, our result is actually not something new over here for this theorem. Anyway, we try to provide a matrix approach by construction, which I personally believe is slightly easier to understand when compared to the proof for the super magic problem. So when P is even, P equal to 2, we have this PQ, PR, and QR with M equal to 26. The magic constant is 26. And when P is 4, we have this PQ, PR, QR with M is 196. And when P is at least 6, let P equal to 2N. And we do it in 2 different steps. We always begin with PQ, PR, QR of size 2. Actually, we refer to the previous PQ, PR, QR over here. And then for every entries in this PQ, PR, QR, we are going to replace it by the magic square of order n. So the integers we use are given by those, as you can see here. So using this method, this is an example for P equal to 6 with M equal to 654. And when P is odd 2n plus 1, we make use of magic square also. And we also define 3 different matrices that we call ABC. And the ij entry for PQ, PR, and also QR are all in terms of the ij entry of the magic square and also the matrix A, B, C respectively. And it's easier to explain by example. So this is what I have when P equals 7. This is our magic square for P equals 7. And this is matrix A, B, and the corresponding PQ, PR. As you can see, there is a very nice pattern for you to extend it to larger value of P. So this is the C and also the corresponding QR. In this way, I get my M is 1036. Okay, so unfortunately, we are not able to get a lot more nice results. So based on what we understand, we would like to believe that most of these PQR boards are actually not Cartersian magic. So next we look at the bi-magic case. For this one, the simplest case is 11R, in which we are able to solve it completely. We say this is bi-magic if and only if R is 1 mod 4, not equal to 1 mod 4. So when R is 0 mod 4, actually we need to assign all together 2R plus 1 integers. And the largest one is assigned to PQ. And the rest are assigned to these PR and QR in blocks of 4 actually. So this is a very nice pattern here. The case for R equal to 2 and 3 mod 4 works quite similarly, but of course we need to make some modification, like swapping, something like that. Okay. So I'll skip the proof also. And for R is 1 mod 4, we can actually conclude that the C3 must be 2R plus 1 to 2R plus 3, only 3 possible values. And for each of these, after some analysis, we are able to conclude that the R must be even, which is a contradiction. Okay. And next, we look at the 2-2R board, and we are able to show that it is bi-magic for even R. And when R is 0 mod 4, this is what we have for the PQ. For PR and QR, we do it in this way. The first 2 rows here is for PR, the next 2 rows is for QR. Again, you can see a nice pattern from 1, 2, 3, 4, 5, 6, 7, 8, and so on. However, our last step is that we have to swap these 2 entries to get our conclusion. So the 2R and 2R plus 2 need to be swapped at the end before we can get the answer. And the case for R equal to 2 mod 4 is also similar, so I'll skip that one also. But unfortunately we are not able to get something interesting for odd part. So like before, we also can show the PPP board is bi-magic for all possible P, and the approach is actually not very different compared to the one for Cartersian magic problems. So we just actually modify the proof that we have just now. So this is a given case. It should be P is even. This is a typo. So when P is equal to 2, this is what we have. And when P is 4, this is also what we have. And for P greater than 4, it works exactly the same as what we have done before. And then for odd P, now this time we define our PQR in a slightly different way. So there is a +1 here, -2 here, +1 here. And in this way we can get the board is bi-magic for odd P. And more general results are given by this theorem 9 and 10 here. Here we have the first one is PPR board. So we show that it is bi-magic when R is P or R is even, and the PRR board is bi-magic for even P. And the next one, we have the condition that P is not equal to R. And we also show that PPR board is Cartersian bi-magic if P is odd and R is even. And also when P is at least 2, PRR board is bi-magic if P is even and R is odd. So over here actually we make use also of certain magic rectangles of suitable size, and we are able to come up with this conclusion also. Based on what we have seen, we would like to believe that most of these PQR boards are actually bi-magic. So I think more interesting is this, the third one, Cartersian tri-magic. And the analysis is generally slightly longer and slightly more complicated. But again, the main idea is still by making use. Okay. So another simple result is that the chi-LA of the complete bipart diagraph K1R actually is just R plus 1, which is at least 3, and R is at least 2. So using these two, we already can make conclusion that chi-LA of this K1 to R, which is the joint of K1R and O2, is less than 4, because it's equal to 3. But 4 is actually less than or equal to this chi-LA of K1R plus 1. In other words, the claim by the original authors is incorrect. And the correct sharp bound should be given by this one. I think I forgot to put down the correct sharp bound. The correct sharp bound should be chi. Okay. Yeah, chi LA of G is greater than or equal to chi G plus 1. So the bound is sharp. The bound is sharp because later on we are able to also determine the chi LA of the joint graph of cycle of n vertices and also n isolated vertices. When both of them are odd, we get 4 here. When both are even, we get 3 here. And note that when m is odd, this chi Cm is equal to 3. When m is even, chi Ca is equal to 2. So this gives us the sharp bound. Okay. In general, we believe that the original claim is correct if we add in one extra condition. That is, if and only if chi G equal to chi LAG. And for sufficiency, it's quite obvious that this is correct. The original claim is correct. However, we are not able to show that the necessity is always correct at the moment, but we do have some other result that shows that for quite a few families of the graph, the sufficiency also is correct. So I'd like to end my talk with these some unsolved cases involving these tri-magic problems. So if I'm not mistaken, after solving all these 4 problems, the problems on tri-magic case will be completely solved, if I'm not mistaken. Frankly speaking, actually, I don't have very deep understanding about application of Cartersian of this magic square in combinatorial design actually. So at the moment, I'm not very sure also, is it possible to find any useful application for this Cartersian magicness in design problems? And hopefully some of us here who attended this conference will be able to find something very interesting or application, or might want to find a good way to further extend it to a higher dimension and something like that. So, all right, thank you very much for your attention.
Are there any questions for the speaker? I have a question.
Yeah.
So I guess so you worked on this and then you found that other paper and then applied it. Is that?
Yeah.
Yeah. How did you stumble upon the other paper, or did someone send it to you? Or?
Actually, someone sent me this original paper. It was sent by this American Mathematical Society asking me to do a review on this paper. So, in order to give a fair review, I have to read it over and over and over again. And at first, I was thinking that the original claim was correct also, until probably after 2 months reading, somehow one day suddenly I have the feeling that I think this is not correct for certain simplest cases. Then from there, I started to find out all the possible counterexamples.
All right. Well, let's thank the speaker, and I guess go enjoy tea.
All right.